Today is day number 10, and we're taking a look again at area and perimeter of polygons. The previous lesson was focused just on rectangles and triangles, so we're extending it now to parallelograms and trapezoids, although to be fair, a lot of the work that we're doing today can be broken back down into rectangles and triangles, just like what we saw yesterday. So the technique is pretty much the same, we're just providing a few additional shapes. So let's start off with the parallelogram. Now before I draw the parallelogram and give the area formula, think about a rectangle. So I'm going to take you back to yesterday, the previous lesson, day 9, and we have a rectangle here with a base and a height, right? And we learned that area is base times height, or length times width if you want to think of it that way. Now what we're going to do is we're going to take this height of the rectangle and let's draw a parallelogram with the exact same height. So in other words, we're going to keep the base the same. I'm just kind of estimating. Let's call that the base. That's exactly the same as the original rectangle, and the opposite side of the rectangle is directly across from the base, but on the parallelogram it's not directly across because, as you know, we have a slant on the side, so the opposite side is not directly across, but you can see that the height of this particular parallelogram is the same as the height of this rectangle. What I'm trying to do is I'm trying to show that this side is congruent to this side, which is congruent to this side, which is congruent to this side. So those are equal bases, just like the rectangle. So what if this was 5 centimeters? This is also 5 centimeters. All right, so we're going to keep that exactly the same. Now the concept here is that we can take this little triangular piece that you see here representing that sort of missing part of the rectangle. We can take that triangular piece, and if you had scissors you could cut that out and tape it on the opposite side like this. And so what we really see here is we see the outline of our parallelogram, right? So the base is exactly the same, the height is exactly the same. This little triangular piece that we've removed, we've taped onto the right side of the rectangle, so now we have this slanted side. That piece is now here. In other words, the area is exactly the same. You still have your height. The slanted side is not the height. The height has to be perpendicular to the base. So there's your height. So the height's the same, the base is the same, so the area is the same. So on your parallelogram, just like the rectangle, base times height, or length times width, is the same area. So let's talk about the trapezoid now. We've seen this shape before. I'm drawing it a couple of different ways. In this particular sketch, I have some right angles. You don't have to have right angles. But we do know that we will have a trapezoid where one pair of opposite sides is parallel and the other pair of opposite sides is not parallel. So we call these the bases. So I'll call this base 1, I'll call this base 2. The other two sides are the legs. But the distance between the top base and the bottom base is the height. And again, the height is always perpendicular to the bases, so that's why you got to have those right angles in there anyway. Now if your trapezoid does not have right angles, such as this one, there's your base, there's your other base, you still need a way to communicate that distance. So again, your height has to be perpendicular to both bases in this case. Either way, we have base 1, base 2, and a height. So the area of our trapezoid is 1/2 of the height times the bases added together. Or you could think of it like the bases added together times the height, all of that divided by 2. So when we get to our shapes, like you can see this hexagon, I've already plotted out those points here. The problem says find the perimeter and the area. Just like yesterday, we could divide it into smaller rectangles and triangles. And there would be nothing wrong with that. We could continue our work with that method, But since we did that yesterday, we're trying to show a little bit of a different technique. And the idea is maybe we could divide this into some other kind of shape instead. In fact, you'll notice point C is directly above point F. So we could connect those two and create a left region and a right region. And we're going to go ahead and do that right now. So if you take a look at this region on the left, do you recognize that shape? That has to be a trapezoid because the left side is parallel to the right side. So those are your two bases. And then the distance between those bases will be the height. And same with the right-hand region. The left-hand side of this trapezoid is parallel to the right-hand side. So those are your bases, base 1, base 2, and then the height is the distance between those bases. So we could further subdivide this into smaller triangles and rectangles, but instead we're just going to use the trapezoids instead. So we'll call this region 1, we'll call this region 2. We'll start off with the area, and then we'll find the perimeter all the way around that hexagon. All right, so area, we have two areas that we're going to calculate, and then we'll add them together for a grand total. So let's talk about our area here. This will be the region number 1, so I'll call it area of region 1, A sub 1. All right, this is our trapezoid. Essentially, you have this here is a height of 1, 2, 3. This here is a, I said height, maybe I should say length. That's a length of 3. This is a length of 1, 2, 3, 4, 5, 6, 7, 8, 9. Because this is the height, we want to know what is this distance from the base on the left to the base on the right. And that is a height of 1, 2, 3, 4. So if we think about our trapezoid formula, we want 1/2 times the height. Again, the height is sideways, the trapezoid is on its side. And then here are your two bases added together. All right, so 3 and 9 is 12. And they're all being multiplied together. So it doesn't matter if you take half of 4 first, or if you multiply 4 and 12 and take half later. I'm going to take half of 4 right now and get 2. And then we're going to go 2 and 12, and that gives us 24 square units. So that's the region number 1. So region number 2, I'm going to move my paper here in just a moment. I'm just getting a head start on the sketch. All right, so just kind of looking at that, we have, again, this side of the trapezoid, which we already counted as 9. Let's double check. Yeah, so that's the 9. This right side is 5. And again, the height is the distance between those bases. I count 6. So our formula is 1/2 times the height of 6 times the bases added together, 9 and 5. So half of 6 is 3, 9 and 5 is 14. 3 and 14 will give us 42. And then we have to add these two regions together to get the grand total. So I'll call it A sub t for total. This is the total area. We're going to add together the 24 and the 42. And that will give us a result of 66. And don't forget the units. Again, it's an area, so we want square units. So that method is very similar to what we did yesterday. The perimeter is also very similar to what we did yesterday. We're going to find the length of each side and add up all of the sides. Now, this is not a side. We're not adding up this 9 to the perimeter because this is a diagonal, right? Diagonals are on the inside, sides are on the outside, so we're going to add up these 6 outer edges, those distances. And for the vertical side, we can just count that as a distance of 1, 2, 3, and the right-hand side is also a distance of 5. It's the slanted sides that will take a bit more time. So I did that already just to speed it up a little bit, and you can freeze the picture and copy that down if you need. What we're looking at here is the distance formula for all the slanted sides. So this is the leftmost side, the vertical edge that we could just count. This is the rightmost edge, again, vertical, so we could count. But each of these four were all slanted, and of course we cannot count. So we're using the coordinate points with the distance formula to calculate all of those. Since we've been doing lots of distance formula, I didn't think we had to work through that step by step, but you can see the answers are here. So BC is a length of 5, CD is a length of 6.71, EF is a length of 6.08, and FA is a length of 5. Then we're going to add up all of those edge lengths. We should have 6 because it's a hexagon. 1, 2, 3, 4, 5, 6. And when we add them up, that will be a length in units, not square units, just linear units, regular units. So the new work is on the back side. I'm going to flip this over and we're going to take a look at a few more examples on the back side here so that we can take a look at some additional problem types. What's different is that we're taking a look at starting off with the total area, and we're trying to work backwards to find a missing dimension. All right, so when we're talking about the area of a triangle, for example, we often use words like base and height. Those are dimensions. So we have the base dimension, we do not have the height dimension. That's what we're going to solve for. So we're going to start off with the formula, substitute in the values we already have, and work backwards to find what we don't. So the formula for the area of a triangle is 1/2 base times height. Or you could think of it like base times height divided by 2. And they're telling me the area is 48, so that'll go in the left-hand side here. The total area is 48. The base is 9 inches, but the height is unknown, and that's the variable we're trying to solve for. Now, you could take 1/2 of 9. That'd give you 4.5. That's fine. Our calculator can handle that. But remember, also you have the option of doubling both sides, and that's how you get rid of the fraction 1/2. Multiply both sides by 2, in other words. And so we get 96 equals 9x. And then we'll divide both sides by 9 to isolate the variable. I believe we should get a decimal answer here. Now don't walk away too soon. Think about the units. You can see it's printed here nicely for us anyway. If the area was inches squared and the base was in inches, then the height should also be in inches because this is not an area. It is a dimension. It is our height, if you want to think of it that way. So let's try that now with the trapezoid. Again, they're giving us a total area, and we're trying to work backwards to find the missing dimension, the height again. The 22 inches that you see here, that is the entire length of that side of the trapezoid. That's one of our bases, and then the 10 is the other base. Those are meant to be the parallel bases. So here's the formula. Area is 1/2 times the height, right, times the bases added together. So let's plug in what we know. We have 100 for the area. There's the 1/2. The height is unknown. That's our variable. We have a base of 22 and another base of 10. So order of operations says we should add these together first inside the parentheses. And now these are all being multiplied together. So again, we have some options. We could multiply both sides by 2 to get rid of the 1/2. We could multiply 1/2 of 32. We have some options here. Doesn't matter which way we go. I'll multiply both sides by 2 like this. So we get 200 equals the x times the 32. And then to isolate the variable, let's divide both sides by 32. Now again, this is a dimension, which means it's a linear distance. So it's not square units, it's not an area, it's a linear. So we want inches on that one. Here are a couple other problem types to finish this off. Example number 4, let's go to a parallelogram now. And let's say it has an area of 60 square feet. Right? You have a base, you have a certain height. And the question is, list the possible dimensions. Again, the base is a dimension, the height is a dimension, and we know the area is base times height. So what we're saying really is we're saying what base times what height would get you an area of 60 square feet. So in other words, we're just listing our factors. Factors are numbers that are multiplied together. So we could have 1 times 60, right? We could have 2 times 30. We could have 3 times 20. All right, so it turns out there's lots of different possible factors, and those are all dimensions, right? So in other words, it's a base of 1 foot times the height of 60 feet, or a base of 2 feet times the height of 30 feet, or a base of 3 feet times the height of 20 feet. And those can swap around the other way around. So it could be base times height. We could have a base of 60 feet times the height of 1 foot. Those are dimensions, the different factor combinations that would multiply out to get us to 60. So there's some others as well, like 6 times 10, you might recognize that one, 15 times 4. So we have a few others. I don't know if I have them all listed here, but I think we could probably get most of them with that list right there. So there's your list of base times height. Let me know if I missed any. We should be able to find some others too. Notice also that typically when we're talking about dimensions, we could include decimal values, but we don't have to. We're mostly focused on the integers, and that's why I'm saying there could be others, implying that we could have decimal dimensions, but we'll just stick with these integers. All right, here's our last example. This time we're jumping back to a right triangle. Because we can take these bigger polygons and subdivide them into smaller rectangles and triangles, it's good to come back and think about some properties of a triangle. All right, so there's your right triangle. Here it says your hypotenuse is 14. Right, so the hypotenuse is always opposite the right angle. There's your hypotenuse. And that means the other two sides are legs. That's a leg, that's a leg. They could be the same size or they could be different sizes. In this case, we have a leg of length 5. It doesn't matter which one. Let's call that 5. Now, if we're trying to find the area, you know you need the base and you need the height. So we have the height, but we don't have the base. So we first of all have to find the base of the triangle. Then we can calculate the area. We could even calculate the perimeter if we had to. But we have to find this first. So this is coming back to our Pythagorean theorem, right? The legs get the A and the B. The hypotenuse always gets the letter C. So A squared plus B squared equals C squared. For us means that we'll have 5 squared plus, well, we don't have the base, so that's our variable. B squared equals 14 squared. So 5 squared is 25, 14 squared is 196. Let's subtract 25 from both sides, moving all the constant terms to the right-hand side. And we have b squared equals 171. So that is not a perfect square. We don't have any factors that are perfect squares either, so we can't simplify that. Besides, if we want an area, we would like even a decimal value so that we can calculate the area. And it even tells us to round to the nearest hundredth. So that means decimals are fine. So let's calculate the value of b by taking the square root of both sides. And we're going to round to 2 decimal places, so it's going to be about 13.08. So this is an approximate value, of course, which means our answer will be an approximate value. It won't be exact, but it should be close. Our area is 1/2 base times height. So my base is the 13.08, and the height is the 5. So I get 32.7 as a matter of fact. There's no other decimal value there because we had rounded earlier. And we have, I don't see any units here, so let's go with square units.